Okay, we're to our last example in section 2.5 on continuity. Before I do example 17, though, I want to look at theorem 11 together. This is called the intermediate value theorem for continuous functions. It says that if f is a continuous function on a closed interval, a to b, so I'm looking at this interval from a to b, I'm including the endpoints a and b, and f is continuous. So here's just an imaginary continuous function through there. And if y naught is any value between f of a and f of b, so y naught is any value between the function at the two endpoints of the interval a and b, then y naught equals f of c for some c that's in here. So in other words, this value of y naught has to be f of c for c some value between a and b. And with the picture, it's like it just makes common sense that that is the case. Of course, I'm not going to prove that. It's hard to analytically prove it, but with the picture, I hope that just makes some common sense to you. So how can I use this intermediate value theorem to do something? So here's one of the more of the abstract type problems I would ask you. In this example, example 17 says, show that there is a root of the equation x cubed minus x minus 1 equals 0 between x equals 1 and x equals 2. In other words, we're asking to show that there is some value of x that makes this function equal to 0, the function f of x equals x cubed minus x equals 1, minus 1, where that function is equal to 0. There's some value of x that makes it 0 where x is between 1 and 2. So what we do is we look at what is the value of the function at 1 and at 2. And notice that the function value at 1 is minus 1, which is a negative number, and the function value at 2 is 5, which is a positive number. That means that the function must cross the x-axis somewhere between 1 and 2. It has to, because it's negative at x equals 1, and it's negative and it's positive at x equals 2. Thus, to get from negative to positive, it's got to cross the x-axis, which is where y is equal to 0. So therefore, it has at least one solution. Now, it could cross it several times. That's not enough to show that it doesn't cross it more than once. I mean, it could cross it several times, but it does tell us that it has at least one solution in that interval 1 to 2.